Thank you. Okay, that's great. Okay, so good morning, Alyssa. Good morning, Vivian. Hello, Daniela. Good morning, Charlie. Good morning, Sawad. Good morning, Noel. Thank you, Daniela. Thank you, Vivian. Thank you, Alyssa. Thank you, Sawad. Okay, great. And I'm going to check. So we're going to actually, while I'm still getting, sorry, we didn't have class Monday. I think you saw, well, I did see that most of you saw synchronized class Monday, but hopefully you saw those videos that were posted. Again, if we're not looking for proof in a court of law or something like that, but like once in good faith, you've watched each one of those videos or any one of those videos you watch in good faith or watch to some extent, watch in good faith, just tell me in good faith that you've watched it. You can use that same assignment portal just to indicate. I mean, you can screenshot or do something to show that you got something out of the material, but for each one that you do, I give you the number of points that I said in the thing. And there's 3 of them, partly because to make up for a lot of class time, like hopefully that catches us up with some of the classes that I've missed or whatever. And I'm going to, but I am going to assume, I'm giving you points because I know it's hard and annoying to have to watch things on your own and stuff, but it is our class material. So I'm going to assume, as we wrap up the semester that you have just made some attempt to absorb that material. Hold on one second. I'm just checking something again. Sorry about this. Sorry. Okay. Okay, I'm just looking at chat. I'm sorry, I know I'm. Oh, no problem. Direct chat person totally got. Okay, yeah. Okay. So again, I don't know that we have. I know we don't have that many more classes. And there's not that much more material that we're going to attempt to do, but there is some material. So I'm just going to keep going with it here. I'm going to ask you a couple of questions. First of all, and I really appreciate how indulgent and flexible and patient you've been with the exams. I presume that, well, certainly all of you who are sitting here have gotten them back, I believe, yeah, all of you who are here today. I mean, everybody's gotten them back. Everybody's gotten them back in this class. So, and yes, okay, good. And I don't want to get into a whole discussion of them right now. Like, I think they mostly speak for themselves. Obvious. Well, I'll say this, I take off points when I take off points, and then I just at the bottom right-hand corner of every page, I just have like a little slash and the total number of points deducted from that page. And then I just add all those up and subtract from 100, and that's your raw score on the exam. You certainly on your own time should check that I did my math correctly. If I didn't, bring it to my attention. Of course, if you have any questions about my handwriting or any place I took off points, of course, you can ask me direct, like not in this class right now, or not in class. I don't think it's a useful, I don't think it's a good use of public time, but certainly if you have any issues with your exam at any point before the end of the year, you can make an appointment with me. We can discuss whatever. Again, it's the same thing as always, which is that I'm looking for you to do well, not for you to do badly. So if I made a mistake, or if there's something you don't understand, as long as you present it to me in the form of a question, or text me and say, I'd like a 10-minute phone call with you about this or whatever, totally fine. Like, as long as it's a question, I might have made a mistake and we can resolve it, and I'd be just as happy as you to resolve it in your favor. Just, please, hopefully let's just not come at it. And I don't think this will happen in this group. I don't see any reason, but just as long as you come at me with an open inquiry, then if there's an issue, we'll resolve it. Like, in other words, these numbers, I might have made a mistake somewhere, but I'm looking for you to do well. And again, you get my point. But there's no statute of limitations on that. You take your time, as long as it's before the end of the final exam. If there was an issue on it, just let me know. I think you all did really well. Even those of you who think you didn't do well, even those of you who think you did worse than you wanted or expected, I think the numbers were actually unusually high, to tell you the truth. They were high. And I think you're all going to do well in this class, even though, and I know there's a couple of people in the room who probably did worse than they expected or they wanted. I get that. You can talk to me. Maybe I did make errors. We'll straighten out. But actually, there was no number in there. There was no number at all that anybody got back that I found shocking or appalling, or think that you should find shocking or appalling. And certainly no number, I could tell you this, I don't want to like dwell the whole day, but I can tell you this, there was no number in there that precludes anybody from getting an A or something like that. No matter what you got on this exam, well, depending on what you're doing in lab and all other things, and depending on what happens in the final exam, I think everybody in the room still could potentially get at least an A-. I believe I can say that. Anyway, so that's to all your credits. Let me just look in the chat. I'm sorry they took so long to get back, but hopefully you have them now. And there's some other numbers I still have to get back to you before the end of the year, but that was the main one. Okay, cool. I'm just looking at the chat. Okay, all right. So again, I just want to move on with material. One question though, and I know I asked you this last week, just because we're getting toward the end of the year and I'm concerned about putting all the material together, but you might be even more concerned about like your grades and moving on in your life, which I understand. Therefore, can you remind me or tell me in the chat, is there anything left for you due in lab? Like any big thing left due in lab? And if so, what is it? Because it might affect how I teach. I mean, I have a plan for today, but I might alter it depending on what you have left due in lab. So if anybody could tell me, and if you have nothing left due, that's fine. Formal report 4 and 5. You have formal report 4 and 5. Okay. Good to know, 4 and 5. And, oh, I remember right, because there was a funny, and 5 is the slow down lab. Yes, the inclined plane thing. Is that correct? Yes. Okay, cool. And 4 was, the projectile one, right? The one that's sort of like the exam question, the one off the table marble one. Yes. Okay. All right. That means that what I'm going to continue today is I'm going to explain one of our last topics, and a topic that I think, again, is very relevant to Lab 5. I know I've, in a way, directed a lot of my attention towards Lab 5. I think it is a very big lab. I think there's a lot going on there. I think it's not easy. I also think it's super interesting for what it's worth, but it's probably more interesting if you don't feel confused by it. So what I'm going to talk about today that has a lot to do with Lab 5 is friction. Okay. Again, stop me if I'm in any way making assumptions that are like wrong. But when I picture Lab 5, and also in case you happen to be listening and you're not like part of the lab program or something, like Lab 5 is a rough inclined plane, right? It's a slide. It's something that moves up a slide and down a slide and experiences not only some component of gravity, but also of friction. So I want to talk, I want to talk today about the friction piece. Ah. Okay. I think I've said this once last time. Oh, once I'll say one other thing. Okay, I started saying this last Wednesday, right? Whenever you have two surfaces push against each other, we represent that interaction in the system schema with two lines rather than one line. Like every other force, well, every other interaction in the system schema is represented with one line. That is to say, every force is represented with one line. Every push or pull is represented with one line in the system schema. Generally, every time you see a line, what that means is a touch. The only exception to that is gravity, where there is a line because there is a pull, but there's no touch, right? So gravity is one exception to the one touch, one line rule for system schemas. Gravity is one exception because it is one line with no touch at all. The other exception to the one line, one touch rule, and that rule is just a silly way, it's just a diagrammatic way of trying to drum into us all that whenever we're trying to picture forces, which is a big thing in physics, like picturing whether a force is happening or not, to picture a force, you got to picture two objects interacting, and to picture them interacting, generally speaking, we picture them touching. I mean, if you want to know whether they're interacting or not, you picture them touching. So generally, if there's a touch, there's a force. If there's a force, then there's a touch. One exception to that is gravity, where there is a force with no touch. The other exception is what I'm discussing right now. The other exception, an exception sort of in the other direction, is that when surfaces push on each other, now they do touch. When surfaces push on each other, they most certainly touch. So it's much more like sort of obvious and vivid that in a way that a force is happening than when gravity occurs. But when surfaces, when realistic rough surfaces push against each other, actually two forces occur. That's really what I'm trying to say, is that the one area in life where we can observe a touch or we can observe physical interaction, but really when we really get down and think about it, drill down on it, we have to realize there's actually two relevant forces going on. There's really interactions going on in two different directions along two different axes, which is why in a system schema, if two surfaces are pushing against each other, in any two surfaces at all are pushing against each other, we actually draw two lines in the system schema, because what we're recognizing is that when rough surfaces push against each other, they also push along each other, like automatically. Because if they're rough at all, and I know I said this last Wednesday, I just really want to there's a lot of reasons to just drill this in. When two rough surfaces push against each other, if you think about the roughness of the surfaces, if you zoom in your mind or picture them microscopically, you realize that there's lots of bumps and ridges on each surface, and these bumps and ridges really are like electrons, all in different places. And the bumps and ridges are interlocking with one another. And the more bumpy, ridgy they are, the more they interlock. So the more you squeeze them together, the more they interlock. So when we push rough surfaces together, we also make it harder for them to slide along each other. I keep saying when we push surfaces against each other, that you might, if we're not careful, you might think that's like all the contact forces in the world. What I'm saying though, I'm trying to distinguish, first of all, pushes from pulls. When objects pull on each other, this doesn't happen. For example, if you pull a fish with a string, or you push, or you pull, you tow a car with a tow rope, like that's pulling, not pushing. And also that's a line, that's not a surface, right? So I'm very, very specifically saying when you have like planes, areas, two-dimensional objects, and they're actually pushing, pressing against each other, then we get a push. Okay, so then whenever we have two surfaces pushing against each other, like my two hands right now, right? Whatever we picture this Euclidean plane, like a thin rectangle or whatever, like we picture a surface, an invisible, infinitesimal surface between those two that we call the plane of contact. So it's like if my two hands are like pieces of bread, I picture this infinitesimal piece of bologna between the two breads, and I picture the two pieces of bread like sandwiching that bologna or salami, whatever, piece of cheese, that thing in the middle is the plane of contact. And I'm saying that the component of push that's perpendicular to that plane, the push against, is what we call normal, or in fact, we generally call the normal force. Normal, because normal in mathematics means perpendicular. And honestly, that's all it means here. One of the reasons I'm making a big deal of this is because in tons of diagrams, as you may have already seen, in tons of contexts in physics, and you may remember this from high school, and it will come up again later on in life, in any physics that comes up, the normal force is something that comes up like all the time in physics. And it's called the normal force. But what that makes people think is it's like normal, like it's normally always there or something. I want to drill into everybody right now that normal means perpendicular. It's sort of a misleading term. In fact, it's like a very misleading term. There are lots of situations in physics where there's no normal force at all, such as free fall. There's no normal force there. Or such as me pulling something while it's subject to gravity. If there's no pushes, there's no normal. Normal only comes into play when surfaces are pushing against each other. When surfaces are pushing against each other, the component of push that is perpendicular to the plane of contact between the two surfaces is what we call the normal force. The normal force obeys Newton's third law. The normal force obeys Newton's third law in that if I push against a wall, I would call that a normal force. Like if my hand pushes against a wall, I would say that my hand is exerting a normal force on the wall. If I'm pushing the wall to the south, then my hand is exerting a normal force on the wall in the south direction. If I were to draw a free body diagram of the wall, there'd be an arrow pointing south on that wall, indicating something is pushing it in a normal kind of way to the south. But similarly, by Newton's third law, if I'm pushing the wall to the south, then the wall is pushing my hand to the north. Like if I push you, you push me back. The normal is like any other force. It automatically goes in both directions. The both directions would be in two different diagrams. Like the free body diagram, the isolated diagram of what's happening to the wall would have all the forces happening to the wall in it. And the isolated free body diagram of my hand would have all the forces happening to my hand on it. So okay, so I push the wall, that goes in one diagram. The wall pushes me back, that goes in a different diagram. That interaction is called normal. What I'm saying here, and I'm going to turn the page in a moment and start doing the math. This, what I'm saying here is that realistically, if the wall is rough at all, and if my hand is rough at all, then by going like this, I'm making it hard for my hands and the wall to go like that. I'm creating another force on the other axis, the axis that is parallel to the plane of contact. That push, that resulting or corresponding push on the parallel axis, the axis that is parallel to the plane of contact between my hand and the wall, that is called friction. And honestly, in a way, that's all that friction is. Friction is the pushing, is the component of push between two surfaces parallel to the plane of contact between those surfaces, and normal is the component of push between two surfaces perpendicular to the plane of contact between those two surfaces. So friction and normal go hand in hand with each other. In fact, let me go a step further and I'll show you the math. This is why whenever you have two rough surfaces pushing on each other, we always draw two, or at least I always draw two lines there in the system schema to indicate right away there's going to be two interactions going on here. Let me also say that the whole purpose of the system schema is to identify what the forces are. Every line that's in the system schema is a force. And what's the point of that? Then when we go to draw a free body diagram, when we go to just draw arrows, when we see this in the system schema, we're just trying to identify forces. Like, what are they? How many are there? But we're not trying to get into any further detail than that. We're not worrying about direction, for example. We ultimately need the direction of forces to plug into F net equals ma, to plug into the left side of Newton's second law. So from the system schema, we draw a free body diagram. A free body diagram represents each force as an arrow pointing in a particular direction. By the time you get to the free body diagram, you're focusing on direction, and you're just drawing all of the forces that are actually acting on a particular object. You're no longer worrying about all the other objects it interacts with. You only worried about those in the system schema to find out what the forces are. Now in the free body diagram, you just put in a bunch of arrows, vectors, indicating pushes or pulls that are occurring to a certain object, your object of focus, your M, the object whose acceleration you're going to study. And what I'm long-windedly trying to say is that the number of arrows in your free body diagram had better be precisely the number of lines that was in your system schema. That's honestly actually the purpose of the system schema. However many lines you generate there, each one of them becomes an arrow. Each, literally one of them, becomes an arrow in the free body diagram. And that's why it's important to, if you have two surfaces pushing each other in the system schema, you draw two lines between them, because now each one of those lines is going to become an arrow in the free body diagram. And those two arrows, I guarantee you, are going to point perpendicularly to each other. The friction will point one way, and the normal will point along a perpendicular axis. They are, by definition, the two perpendicular components of one overall phenomenon known as surfaces pushing. So, again, long-windedly to say. So what I'm really saying is you can't have friction occurring at all without a normal force. Friction occurs when two surfaces are pushing against each other. As long as they're rough and they push against each other, there will be friction. What I'm really saying then is friction is the result of two things: how rough two surfaces are and how hard they push against each other. We can capture that mathematically in the following way. Okay. Okay. So how much friction there is between my two hands results from how hard my hands are pushing against each other and how rough my hands are. Roughness of material is expressed in, measured in, captured by something that we call the coefficient of friction. Okay, the coefficient of friction is designated by the lowercase Greek letter mu, I should say. Mu, it looks sort of like an M and sort of like a U put together, whatever. Mu is the coefficient of friction. There's actually two types of mu. I might get into that in a minute, I might not, but mu is the coefficient of friction. It's a coefficient in that it's a simple number, in fact, a fraction or a decimal, greater than or equal to 0, but usually less than or equal to 1. Like technically, there's no law that says it can't be greater than 1, but in almost all cases, it's less than or equal to 1. So mu, for the moment, you could think of mu as almost just like a rating system for roughness, like something that's perfectly smooth, perfectly unrough, like a vacuum or like an air hockey table would have a mu. And you might want to, I don't know, if you want to just jot this down for perspective, like the cushion of air on an air hockey table would have a mu of almost 0, like 0.0001 or something like that. Then like waxed polished skis or like ice, really Zamboni ice or glass or something would have like a mu of like 0.05 or 0.1 or something like. Oops, sorry. And then wait, I think someone's sorry. And then it gets higher and higher. So then like smooth polished, really polished formica or why can I not, or some kind of metal would be like 0.2, and then things get rougher and rougher. So like wood would be like 0.3 or 0.4, and then you get all the way up to like rubber would be like 0.9. Okay, so so mu is just a number that rates how rough something is. And once you'll it's a simple number between 0 and 1. It's almost like a grading scale or a rating scale for roughness. It almost seems very scientific that way. But then more specifically, it's truly a coefficient. Mu really is a coefficient in that it is a pure number. The units of mu are not. There are no units of mu. It's unitless, because what mu really is a ratio of newtons to newtons. It's a ratio of force to force. I'm going to show you now on the next page. And the newtons cancel out. So so roughness coefficients, friction coefficients are literally coefficients, like just a pure number between 0 and 0.9999. Let me just so that. Okay, now how does this work, or where do we get mu, or what do we do with it? The point of mu is this. What mu, sorry. I'm going to start by just saying, just for like notation purposes, I'm going to use lowercase f. In fact, let me even be more clear if I can. I'm going to use lowercase script f. I mean, you could do whatever you want in your notes. I'm just telling you how to read my notes. I'm going to use lowercase f to stand for force of friction. Like I'm not like, because capital F tends to mean force just in general. So here I'm talking about the force of friction. I'm going to use lowercase script f to mean force of friction. And I'm reminding you that the units in which any force is ever measured in, but including the force of friction, is always measured in newtons So I'm going to use a capital script N to mean newtons now. In fact, if it, I don't mean to be inconsistent. We can even do that back here. I apologize. I just didn't know if you know what I meant if I did it back here. Sorry, I'm not trying to be, but I am, I guess. So I'm using, what I tend to do is use lowercase, capital script N to mean newtons, which is the unit in which a friction is measured. Then normal force, I'm going to use capital N with serifs, like Times Roman, whatever. Capital N to mean normal force. It is also a force. It's also measured in newtons with a script N. A little bit confusing. That's why I'm just trying to make the notation clear here. So, because there's like a lot of N's flying around and a lot of F's flying around. Okay, if I use that notation, that lowercase script F means force of friction, and we recognize that it's measured in newtons. And if I use capital N with the serifs to mean normal force, and that's measured in newtons, then what mu really is, then mu is defined to be the ratio of friction force per normal force, i.e., and this is almost exactly what was written on the front page when we started today. Friction is fun. What I'm saying here, and you could think of it, as a triple equal sign definition, or you could think of it as a resulting equation. What I'm saying here is mu is the ratio of how much friction you get per each newton of normal force. It's how much rubbing you get per each application of pressure, of pressing, right? One last way to put it. So in a way, it's just a pure definition. It's just what would happen if okay. What I'm saying is, just imagine a simple experiment or something where you have a block on a table and you start pushing on the block and you measure your push in newtons. You start sandwiching the block against the table and you measure that in newtons. And first you apply 1 newton of force of normal force between the block and the table. And then you measure the resulting friction that is experienced between the block and the table. Like you push it down and then you try to slide it over and you see how hard it is to slide over. And then you push for 2 newtons of force along the normal line. And then you measure and see how hard it is to slide across the other axis. So if you were to imagine doing a controlled experiment like this, like steadily increasing the normal force, the squeeze, the pressure between 2 objects, and then measuring the resulting frictional sliding resistance between the 2 objects. If you were to do an experiment like this, where your independent variable was the normal force, and what you're watching in response to that independent variable is the dependent variable of frictional force. If you were to make a series of measurements like this, what you find within reasonable cases, within reasonable circumstances, we're fortunate that we would basically find a straight line, a linear direct proportionality relationship. That basically, if you double the squeeze between 2 objects, you'll double the sliding resistance between those 2 objects. And if you triple, you'll triple. That's what we find. That friction, in other words, remember I said 2 minutes ago, friction depends on roughness and on normal force. Well, it turns out that friction linearly depends on normal force. Like they really are intimately related. The more hard you squeeze 2 objects, the more hard they are to rub against each other. They're really linearly related, which is nice. Within reason, to a point. So one is directly proportional on the other. The constant of proportionality, the slope of that graph is what I'm trying to say in this rough sketch over here. The slope of that graph, the rise in friction force that you get in correspondence with the run in normal force, that essentially constant slope is the roughness of the materials, is what we call mu. In other words, if you between any two objects, if you double the normal force, you'll double the friction force. But it's like y equals mx plus b, where b is 0. But exactly how much friction will you get for the normal force? Well, that totally depends on how rough the objects are. If the objects are rougher, the slope of that line is steeper, is higher. You see what I'm saying? It's a straight line no matter what. But the rougher the objects, the steeper the line. So friction equals mu times the normal is kind of like saying y equals mx plus b. I mean, it is saying y equals mx plus b, where b is 0, and where x is the normal force, y is the friction force, and m, the slope, the constant of proportionality, is the roughness of the two materials. So ultimately, what I'm saying here is exactly what I said 2 pages ago, but now I'm saying it mathematically. I'm saying if you want to know how hard the friction force is that one surface exerts on another, what you need to know is 2 things. You need to know how hard they're squeezing on each other in newtons, and you need to know how rough they are in pure units, as a pure number. Multiply those 2 things together, and you have the friction force. Lastly, another way I'm saying it is mu is a coefficient of roughness. Mu is, okay, I'll write this because it's a common mistake that people make, especially in lab 4, I guess. No. Mu is the coefficient of roughness. It's a coefficient of friction. Mu is not a friction force. Mu, if I tell you that the mu of a hockey puck on a wood table is 0.2, that does not tell you the friction force that the hockey table is exerting on the hockey puck. It doesn't tell you anything about newtons. It's telling you how rough the surfaces are. You multiply that roughness by the other thing you need to know, which is how hard the 2 objects are pushing on each other. Multiply the pure number times the number of newtons of normal force, and you'll get the number of newtons of friction force. That's how this works, okay? Let me, okay, just look at the time, okay. Oh, just also last note of caution. I'm going to keep going on with this and try to apply it to a lot of stuff. Last note of caution, the normal force is whatever it is for any given situation. Sometimes it's 0. I mean, like sometimes there is no normal force. There's no formula. I mean, please note this. This is another common mistake people make either in lab 4 or sometimes on the final exam. There is no formula or equation to memorize for what the normal force is. If you try to look one up on the web and you find one, it's even worse than if you don't find one. Because if you don't find one on the web, that's because there isn't one. If you do find a formula for memorizing the normal force on the web, then I guarantee you it's wrong and misleading, will get you into trouble. The normal force, for example, what I'm really trying to say is do not, please, if you're paying attention right now, do not think that the normal force always equals the gravitational force or always equals the weight of an object. I tried to get into this in the videos that I hope you watch. It's very easy to get fooled by Google or by textbooks. And I'm not saying anybody's lying. I'm just saying the material can get confusing, and it can look like, it can seem like normal always equals mg or something like that. Like at this point in the year, often people are sort of falling into that misconception. And if you've never heard, if you don't even know what I'm talking about, just ignore me. Like really, I mean, like my family. But I'm saying if you don't think that the normal force automatically equals anything, specifically, especially don't think the normal force always equals the weight of an object. It could have nothing to do with the weight of an object, particularly if you're pushing something at an angle or you're pushing it purely horizontally. The normal is whatever it is as determined by Newton's second and third laws. So we're going to do examples of that, but last thing I guess I'm saying is a lot of the work that we often do in dynamic problems is setting up our diagrams and our math explicitly so that we can figure out what the normal force is. That's like a quest. Don't think of that as something you're missing. Like that's like usually the issue in physics problems is figuring out in exactly what the normal force is equal to so that it can be plugged into the friction force. And then that can be figured out. Okay. Couple more notes on this, and then we'll get to application. Okay, sorry. So there's really two types of friction. Okay, one type of, or we divide our understanding of friction into sort of two cases. One case is when one surface is already in motion relative to the other surface. When there's sliding, such as in lab 4, when your object is sliding up the inclined plane or sliding down the inclined plane. Whenever we see two surfaces pushing against each other and they actually are sliding relative to each other, when one object has a velocity, a non-zero velocity relative to the other, we call that sliding friction or kinetic friction. In other words, it's friction acting when to oppose motion that's already in place. Okay. And so technically we call that kinetic friction, F sub K. And what it's equal to is mu sub K times the normal. That is to say, when I said a moment ago on a page ago that surfaces have a coefficient that designates how rough they are, the truth of the matter is they have two different coefficients. And I'm about to give you, I'll give you the second one right after this. One coefficient is called mu K. That's how rough they are and how they act in response to a situation of already present sliding. Mu K is just a number between 0 and 0.9 and has no units and all that. But so technically, mu K times the normal will give you the friction force, magnitude, the magnitude. And so that's what A is there, the magnitude of the friction force, in this case of kinetic friction. The direction of the friction force, in a way, is exactly what you would think, but I want to say it in physics terms, because it does become very interesting. The direction of friction, it does what you think. It opposes motion. But remember now, what we're trying to drive in the course here is that motion, velocity particularly, is a relational idea. There's no such thing as a velocity of an object by itself. There's the velocity of an object relative to another object. So if two surfaces are in motion relative to each other, the way friction acts is the friction, the push of surface A on surface B will oppose the velocity of surface B relative to surface A. In some ways, it's exactly obvious. It's exactly what you would think. It probably sounds like more words than is necessary for what you would think. But in other ways, it's very important that I point this out. In other words, the friction that the inclined plane exerts on your object, if the object is sliding up the inclined plane, then the inclined plane will exert friction on the object pointing down. It will oppose the motion of the object relative to the inclined plane. What I'm saying is the whole inclined plane might be moving through the lab while this is happening, and that will not in any way change the interaction I just said. The direction of friction is not objective or determined by the universe. It's determined by the two objects that are in contact with each other. Maybe that's obvious. But having said that, let me move to the other case now. I think it's actually not. Well, anyway, I'll move to the other case now. The other case. Case 2. Hi, in class. Hi. Hi, in class. Oh, hi. Okay, right. Sure. Okay, this is a little bit more confusing. I'm sorry about the interruption. This is a little bit more confusing and subtle and more interesting, perhaps. The other type of friction occurs when one object is stuck relative to another type of object. In fact, it's the type of friction that keeps one object, one surface stuck to another surface. Okay, now this happens all the time in life, in fact, very much so. So like I can have this surface on, I don't know if I can do this without, okay, this surface on this surface right now. This is a very stupid thing to do, but so I have a surface on a surface, right? Right now, maybe nothing's happening at all because like nothing is happening. But see, now if I start tilting the lower surface, if I start tilting this whole thing and making an inclined plane, very delicate operation here. If I make an inclined plane here, kind of like your inclined plane in lab, notice at a certain angle, like right now, there is an angle here. This angle is bigger than 0. There is a component of gravity trying to pull this phone down. Like right now, maybe nothing was trying to move the phone at all. Maybe right now there was no friction at all because there didn't need to be, because like literally nothing is happening, maybe. But right now, clearly, I'm tilting the bottom surface. So right now, I am subjecting the top surface, the black phone. I am, if you can see it, I am subjecting the phone to some kind of component of gravity. There is a net downward pull along the surface of the plane. You know, I mean, there's a component of gravity pulling along the surface of the plane that is trying to yank the phone down right now. And F net equals ma. Newton's second law says the net force on an object, any unbalanced force, any force that's left over after you add up all of the positive and negative components along that axis, any net force should produce acceleration, and it will, right? So there's a net component of gravity pulling my phone down on the white inclined plane here, the white pad, right? If that were the only game in town, if there were no other forces pulling along the white surface, this black phone should definitely be moving. It should be accelerating down along the plane, right? Like literally. And in fact, it's no different. It may be a little bit more exotic or obvious, but it's no different from, whoa, hello, I'm an idiot. It's no different from, right? It's no different from, like right now, if I put this black phone on my hand and I go, and I start blowing on it, if that's the only, even though that's a tiny force, my blowing, even though it's tiny, if it's the only force acting on the phone, if there's nothing opposing it, the phone should accelerate toward the screen. And if I don't want to like overstate this point, but I can't overstate this point. If I push on the phone with my finger at all, it doesn't matter how weak I am. If I push the phone with my finger, that phone should be accelerating toward the screen, but it's not. It's staying in place, right? Like, what is that? Well, that's friction. Yes. I mean, if there's a horizontal force on this phone holding it in place on my hand as I blow on it, if it's horizontal, if it's parallel to the plane of contact, the only thing touching the phone in any kind of horizontal way is my hand. It's got to be, right? I mean, you can't just make up forces. If there's a force acting on my phone horizontally, it's got to be a push or a pull from something that is touching the phone in a kind of horizontal way. And what that could be or is the roughness of my hand. But it seems to be there even when the phone isn't moving at all. There seems to be a kind of friction that kicks into place even when objects are not already rubbing, when they're just sort of trying to rub or slide against each other. We call this static friction. It's so super common. It's sort of like what's holding the whole world together half the time, right? Like I mean, I know it's not a new idea to you, but it is important to actually think it through that static friction, if it's the force of friction that's holding things together, and by the way, if you, I mean, ultimately it's not unrelated to the notion of static electricity, the interaction among all the electrons that are on the outside of all surfaces, like something this has to do with electron repulsion. We'll get into that in physics 204, but static friction, friction that holds things still, must kick in whenever one object is sort of whenever we're trying to move one object relative to another. So static friction kicks in when there isn't velocity between the two objects, but when there's a tendency towards velocity. Why would there be a tendency? Because if there's a net force, if all the other forces, if there's forces along that axis other than friction trying to go in some direction, static friction will automatically kick in to oppose that net force happening along the same axis. The thing is, it's a little bit, so first of all, I'm saying every surface has two different coefficients in truth. It has a coefficient of kinetic friction and it has a coefficient of static friction. Two different numbers, they each function the exact same way. Like each one of them, if you multiply by the normal force, you get a friction force. They never, you might want to write this in the notes, I don't have this here, but they never act at the same time. Two objects are either still relative to each other or they're moving relative to each other. In fact, generally speaking, they're still relative to each other until something gets them moving and then they're moving relative to each other. So it's either static friction that's playing a role or it's kinetic friction that's playing a role. And each one has its own little coefficient. It turns out that, so every surface really can be described by two separate coefficients. Its coefficient of static friction, which is a number, and its coefficient of kinetic friction, which is a separate number. They're very similar types of numbers. The static number is always greater than the kinetic number, or maybe they could be super close, like almost the same. But the static friction number is never smaller than the kinetic number. If you run equations, just play around with this, you'll see why it makes sense. Because if the static number were ever less than the kinetic number, that could mean, it leads to paradox. It would mean that something would be moving and then be resisted so much that it wouldn't be moving, and it doesn't make any sense. But you can play around and see that. But the thing about static friction is, and please note this, whether it's on the exam or not, I don't know, or whether it's in your lab or not, just notice that in the back, I'm giving you two equations that are super similar. I'm saying F is related to mu times N in both cases. But notice in the kinetic case, I'm literally saying an equality. If you, come on, right. The kinetic case, friction sub K is literally exactly, precisely equal to mu sub K times the normal. If you know mu K and you know the normal, you multiply them, boom, you have the kinetic friction. With static friction, it's not an equality. With static friction, it's a less than or equal to. In other words, what I'm saying here is that static friction is a variable force. It gets greater and greater in response to whatever it is that's trying to make things move. So, like with the example, if my hand is an inclined plane and the phone is the object on the inclined plane, I tilt the plane at a little bit of an angle. So I have like mg sine theta pulling down on the object. Well, static friction is pulling up on the object and equals, like right now, what does static friction equal? It equals exactly mg sine theta. It doesn't equal something bigger than that. Like, in other words, like right now, what does static friction equal? Not mu s times the normal. It equals exactly mg sine theta. How do I know? Because if I believe, and I'm thinking you sort of know this from lab 4, and I will get more into this next time with the component, but like there's this component of gravity, not all of gravity, right? All of gravity is pulling straight down. Gravity, the weight of this object is pulling it straight down. Again, also this is in the videos that you're hopefully watching. But so gravity is pulling straight down. A component, that means gravity is doing two jobs. It's pulling the object in by pulling straight down. That means it's to some extent pulling it into my hand and to some extent pulling along my hand, right? Gravity by pulling straight down is doing two jobs, one along the plane and one against or into the plane. If you make the plane like the x-axis in your mind, there's a component like that and there's a component like that. This one's mg sine, I'm saying this quickly, but this is mg sine theta. This is mg cosine theta. Again, I'll try to say that more slowly next time, but I think it's in the videos that I posted from Monday. So if the component, in other words, gravity is doing two jobs. It's trying to keep the object on the plane, against the plane, but it's also trying to pull it along the plane. The component that is pulling it along the plane is mg sine theta. If this object is not sliding down the plane right now, if it's stuck, that's because there's static friction pushing in the other direction, opposing mg sine theta. They must be exactly equal if this thing is not accelerating at all. They are. Right now, mg sine theta down the plane is equal to static friction. If I make the angle a little bit bigger, somehow it's still stuck. Mg sine theta just got a little bit bigger if I make this angle bigger, because theta got bigger, so sine theta got bigger, so mg sine theta got bigger, right? In English, I'm just saying if I tilt this more, gravity is pulling on the object more, but yet the object is still stuck. So static friction must have increased, right? The static friction pulling in the other direction must have increased to match the increased component of weight. Right? Because if gravity were pulling harder than static friction, this thing would slide down. And if static friction were pulling harder than gravity, I don't care that it's called static. If a force up is greater than a force down, then the thing would slide up. F net equals ma. So I'm trying to say static friction is unlike kinetic friction. Static friction is a variable force. It literally increases or decreases to precisely meet the needs of a situation. It's kind of fascinating that it can do that. Ultimately, it's an electron. It's ultimately an electrostatic phenomenon that's happening. But static friction will precisely meet in magnitude the net force of everything else on that same axis, the sum of all the other non-friction forces. Static friction will meet, equal all of that. So static friction, like right now it's zero because nothing's trying to pull this phone at all. The phone's just sitting there because it's just sitting there because like nothing, because Galileo's principle, because Newton's first law, like nothing's trying to do anything to this phone. Then I try to pull the phone down a little. So, hi. Okay. Hi. So, good to see you in the middle of class. Cool. I think I get it. Wait, okay. Slightly confused, but okay. But awesome. Good to see you. I think. I mean, I know. Okay. This thing is sitting still. There's no static friction on it right now. There's no kinetic friction. Then I try to pull a little bit. There's a little bit of mg sine theta. So there's a little bit of static friction pulling back, exactly equaling. Again, also, by the way, not because of Newton's third law, but just because of like reality, right? Yes, awesome. I'll be very psyched. I'll be pumped. Then mg sine theta gets greater. So static friction gets greater. Greater and greater. Static friction keeps doing what it's doing. It does as much as it can possibly do. Static friction doesn't equal anything except other than what it needs to equal until eventually, and I don't want to break my phone, but eventually my angle gets so big. How big does it get? It gets so big that it exceeds the maximum that, the forces opposing static friction get so big that they exceed the maximum that static friction could possibly handle. What is the maximum that static friction could possibly handle? That is what is μs times the normal. Again, please note here, this equation, it's not an equation. It's a less than or equal to. Another way we could write it that's literally equivalent, and for some people this is clear, you could write either way you want. What I'm saying here is that the maximum force of static friction is μs times the normal. Below that threshold, the static friction will be whatever it needs to be. So basically, when you're trying to move things, you push on them to move them. Initially, static friction will oppose, it will do anything it can to hold an object in place. So you push something lightly, it doesn't move. You push harder and harder, static friction will push harder and harder, holding it in place until you push hard enough to demand a force that's greater than the product of the squeeze with the static roughness. And then static friction can't handle it anymore. You break the static friction seal and the object will start moving. What happens then? Static friction disappears entirely and kinetic friction kicks in. It's always one or the other. It's never both at the same time. It's static friction until it no longer can, and then it's kinetic friction forever and ever after that. And it's static friction from zero on bigger and bigger until it no longer can. And then it's kinetic friction at some constant value from then on in. That's how friction works. Okay, a little bit complicated, but that's how friction works. We've got 5 minutes. We've got 5 minutes. So I want to put these friction and kinetic and normal forces into a free body diagram. Okay, I know we only have 2 minutes, so I mean, we will get back to this on Monday or whatever, or in the next video, or sort of we already did in the video. But I just want to make clear now, we talked a lot about system schemas. System schemas are circles interacting via lines, the lines representing the sort of mutual interaction known as force. But even if we only have 1 minute, I want to make clear that the free body diagram, in the free body diagram, you draw a dot. You don't draw a circle. You draw a dot that represents the center of the math. And again, I am watching the clock. Will we end in 1 minute? But just to be clear with free body diagrams, you draw a dot that represents your object of interest. From that dot, you draw a vector representing every force acting on the dot. Like you put the tail of every vector at the dot and the tip goes off in the direction of the actual force. So really what we're doing is in the free body diagram, we're actually focusing on direction. We're actually trying to get direction straight, and we're actually trying to get arrows that we can actually, from which we can actually get quantities, magnitudes, and directions to put into Newton's second law. Like we're trying to generate the math in this diagram. So this diagram has the vectors in it. Therefore, since class is just about over, let me just say this. That really with the FBD, the free body diagram, and again, I'll say this more in the next class, you draw one arrow for every force as it is actually occurring. So if this were the case, this is an example, and we're going to end right now. And I know I've given this example before, but for your lab 4, like there is gravity pulling straight down on your object on an inclined plane. The plane, the normal force of the plane is pushing up at some angle because it's a plane. Friction is also pointing at an angle. So normal force is perpendicular to the plane and friction is parallel to the plane. That would be an example of a pure free body diagram of an object on an inclined plane. You would then, from that, divide up vectors into components so that everything was along, so that every arrow you saw was either along an x-axis or a y-axis, but nothing would be flying off in between. So just again, example, we're done right here. But example, the component would look something like this. I will discuss, and I know in a way this is all, we'll discuss this more on Monday, but I'm just trying to give you the overview. But free body diagrams are only of the forces acting on a given object, where system schemas were lots of pairs of objects. The free body diagram is just the object itself, isolated in a point in time and space. First, we put the pure forces that are actually acting on it, and we divide them up into components so that we can do F net equals MA along the X and independently, simultaneously along the Y. That's it. So I went over 2 minutes. I'm glad you got your test back. The other class will get its test back today too, if anybody here happens to be in the other class listening. Okay, congratulations, you guys, and we will talk more next. Have a great blah, blah, blah. Yes, you too. Thank you, guys. Okay, sorry to keep you late. Thank you. Yes, okay, thank you. Thank you, guys, seriously.